Okay, so why don't we get started? Let me just make a couple of announcements before we start. So lab 2 is done. I have a couple of lablets that I needed to hand out. So I'm going to give the first of those lablets this week, maybe either today or tomorrow. It's going to be on virtualization. That's a concept we had covered some time back. And there's another one on cloud computing that we will also hand out. Once this lablet is done, we'll hand that one out. Both of these concepts you will use in some shape or form in lab 3. Okay, so this is why we are giving out these lablets, so you're familiar with what these concepts are before you start doing the actual lab. All right, so lab 3 should come out soon. I'm not rushing to hand it out, but I will give out the lablets first. All right, okay. So let's continue from where we left off last time. We started talking about logical clocks. Remember, we already covered what clock synchronization does, why it's important. We talked about GPS. We talked about how when you do locationing as part of GPS, you also solve a clock synchronization problem. Okay? And then towards the end, I was talking about any practical clock synchronization technique will have some inbuilt error in it. Okay, so there's going to be no clock synchronization is perfect. There's always some error. So whenever you have two events in a distributed systems that have occurred close to one another, and specifically the difference between those two events is smaller than the error tolerance of your clock synchronization, you cannot often say or conclusively say which event has occurred before which other event. So ordering becomes a problem when you have closely spaced events, regardless of how accurate you make the clock synchronization, it's never going to be perfect. Yeah, so to get around this, we said, is there some other approach? Yeah, and that is where I introduced this concept. Well, we haven't actually introduced it, but I mentioned that there is this concept of a logical clock. And the idea here is we will not use physical clocks to reason about ordering of events. If you only care about event ordering and don't care about the time at which events occurred, then this is a good approach. If you really need to know physical time at which events occur, then you need a physical clock. There is no getting around it. Regardless of all of the issues with clock synchronization techniques, you still need to use physical clock. So here we are only going to be saying this applies to a class of problems where you have events in your system, you want to reason about the ordering. Yeah. And the basic point we want to sort of look at is how do you define a total ordering of all the events in a system? Okay. I'm going to describe this concept of a logical clock, which will actually not give us total ordering. It's going to give us a partial ordering. So we won't exactly solve that problem, but that's what we want to solve. If there was a way to get total ordering without using physical clocks, then this would be a very good approach. Okay. We'll get to some part of that, but not all of it. So we'll have partial ordering. Okay. So how is this going to work? So what we are going to do is we are going to look at properties that are very basic of how applications execute in a distributed systems, how they communicate, and use execution order and use message passing as two basic concepts that can tell us how to order events in a distributed system. Okay. So first assumption is there is no more a global clock. There's no physical clocks we are going to use in the system. Global clock essentially means a perfectly synchronized clock, a single clock that's perfectly synchronized that you can use on all the systems. There is no such thing in the real world anyway, but we'll assume not only is there no global clock, we'll assume there's no clock synchronization at all. So even the physical clocks that exist are unsynchronized. Okay? So we can't use physical clocks and physical clock timestamps to order events because we're assuming there is no clock synchronization at all. Okay? So now in this case, with that set of assumptions, what are we going to use? What are the basic ideas? First thing is when an application executes on a single machine, okay, all events are ordered by execution order. Okay, because we'll assume that you're sequentially executing instructions of your program. Okay, and that sequential order is basically known because that's how we are ordering. And if any statement creates an event, let's say a print statement or any other event, those are ordered. So within a machine, events are ordered because they're ordered specifically by execution order, okay, of those events. Okay, so I'm going to actually draw a picture, hopefully a better one than last time. Okay, so here is timeline. Okay, so this is, let's say, some process or on machine A. So this is time, and some application is executing here, and each of those points are some event that you care about. Okay, and because we are executing this sequentially on a machine, these are all ordered, so that we know. Okay, and then B is another machine. Okay, so here we have another application, and all orders on all events on that machine are also ordered. Okay, so local events are ordered, but we cannot at this point say anything about events across these two machines because there is no clock that tells us what has actually happened. Okay, so we are now going to use a second property, okay, in addition to local events being executed in program order, and that property is message passing. Okay, so we'll assume that applications in a distributed system communicate with each other specifically by sending messages. Okay, this could be socket messages, RPCs. What the messages are is not really important. What is important is there are messages going back and forth. Okay, so message passing is going to give us a very basic property to allow us to order events across machines. Okay, within a machine, events are ordered. Now we want to order events across machines. Then we can order all the events in a distributed system. Okay, so what is the basic property? I mentioned this last time. The message passing itself has two events: the send of the message and the receipt of the message. Okay, the top part is the send, there, or this arrow depicts a message, and then the bottom one is the receipt. Okay, it follows that send has to always happen before the receipt. A message cannot be received before it's sent. Right? I mean, that's laws of physics. So in this case, for that message, the send, which is the top event, has occurred before the bottom one. Okay, so we know that. Okay? Now we also know that events within a single application or a single machine are ordered based on execution order. So what this also means is all the events before the send, okay, are ordered with respect to that send. Okay, so we know all of those events have happened before that send. Okay, and similarly, because of execution order, all the events after the receive have happened after that receive event. Okay, so all the subsequent events are ordered with respect to that event. Okay, now you can use transitivity property, and now you can order events across machines based on this single message. Okay, in particular, all the events on machine A before the send have occurred before all the events on machine B after the receive. Okay, so in particular, all of these events have occurred before all of the events on machine. So those events have happened before these. So now we constructed without any clock synchronization an ordering of events across two machines, just by one message that has gone between those two. Of course, there will be many more messages that go back and forth that will allow us to order other events. Okay, not all events have been ordered. In particular, everything before the receive on B, we don't know how it's related to all those other events on A, and all the events after the send also are not ordered, but maybe there will be other messages that go back and forth that will allow us to do that. Okay, so it's a partial order, but with lots of message passing, you can get some order. Okay, and this is transitive. So there was a third machine C. Okay, let's say there is another message that goes from B to C. Okay, same thing applies. Okay, that send has to have happened before the receive. All the events before the send, okay, have occurred before all the events after the receive. And because this is transitive, you can now order events on C with respect to A, even though there is no explicit messages between A. In particular, all the events before the first send, okay, are ordered with respect to all the events with respect to the second receive. Okay, because those events have occurred before these events have occurred before those other events. So that's transitivity. Okay, yes, question.
Send, I understand Or like even
Yep.
the synchronized clock between the three machines.
Question is the send timestamps in synchronized clock. So if you are using physical clock, all of those events would get timestamps from your clock, right? So you have a clock, you timestamp, just as when you modify a file, it gets a timestamp. Okay, so you will use those timestamps to order events. Here we are assuming there's no timestamps from physical clocks. I haven't shown how we are going to actually get this. This is just a conceptual idea. We'll talk about a technique that allows us to get this ordering, but we are not going to use physical timestamps. Okay, we'll use a logical clock. We'll talk about that. But is the concept clear before I move on? Yes.
What happened like in those paths that is not included?
Okay. Question is what happens on events that are actually after the send and before the receive, right? That's the question. So at this point, with this information we have, if I say here is an event, okay, let's call it X. Okay, here's an event, we'll call that event Y. I say, can you tell anything about these two events? Has X occurred before Y, Y occurred before X? It almost looks like if this is time, Y has occurred before X because it seems like it seems to occur before. But in this case, we cannot tell. They are unordered. There's no relationship we can define. So as far as this picture is concerned, we'll say that X and Y cannot be ordered. You cannot reason about X has happened before Y or Y has happened before X. It could be either of those two. That's what we'll say. Okay. So in other words, either there is a relationship between two events where you say this event has happened before that event, and I know because either they're local events or there's a send of a message and a receive of a message that orders them, then I know the order. And there'll be many other events where they're unordered at this point. We don't know. Okay. Now, on the other hand, if there was a message that went that way, okay, now I have a message from B to A. Okay, now Y and X are ordered because this is a send and that's a receive. Okay, so now in this case, you'll say Y has happened before this send, that send has happened before that receive has happened before X. So Y and X now get ordered if such a message had actually been exchanged. Okay, but without such a message, you cannot see. Is that clear? Okay. So back to where we were. So we are now going to introduce a concept called a logical clock that tells us how to do this. Yes, question.
So those were processes, right? Events on a process can be on, not on a machine.
Okay. Question is, are A, B, and C processes or machines? And are we talking about events within a process or event within a machine? So I left that a little vague. Technically, these are processes. Okay. But for the purpose of today's discussion, we'll use an abstract concept where each process is running on its own machine. Okay. You could have, of course, had two processes. If two processes are running on the same machine, the problem is still easier because those two processes share a physical clock. So you can actually use the physical clock to order this. Okay. So problem only comes when two processes are running on different machines and their clocks are not synchronous. So you can have multiple processes on a machine, then you have a simpler solution to this problem. Use the actual clock because they share a clock, so you can perfectly synchronize them. Okay. All right. So this whole concept that I was talking about basically was something that Leslie Lamport in the 60s or 70s came up with. I don't know if you heard of Lamport. If you use LaTeX, okay, the Lamport actually, that's called Lamport's tech. So he's done a lot of interesting work in distributed systems. It's the first time we are encountering Lamport. We'll see several other concepts in the next few lectures. All of them originated from some ideas that Lamport came up with. So this technique is sometimes called Lamport's clock, sometimes called logical clock. It doesn't really matter, but either name is fine to use. Point is that it is not using any physical clock. Okay, so hold on. So let's see how we can do this. So before we actually come up with a technique to order these events based on some timestamps, we got to define this ordering relationship, which we'll call a happened before. Okay, so usually you use this arrow that's actually shown there. A arrow B basically says A happened before B. Okay, so that's a relationship we want to define. Okay, so as I said, if A and B are events in the same process, and if A executed in that process on that process before B, then clearly A happened before B. Those are local events. I already said that. Okay. So then the second thing is, if A is an event that represents the sending of a message, and B is an event that represents the receipt of the message. So A and B are essentially the send and the receive of the message. Then also we know an ordering between A and B. In this case, also A happens before B. Right? Those are the only two properties we need, okay, for this technique, because that's what I said. Local events are ordered, message passing is ordered. Okay? And we say that this relationship is transitive. If you know there are the three events A, B, and C, and you're told that A has happened before B and B has happened before C, then A has happened before C. Okay? So that's essentially relationship transitive. And last question or point, which was the question of us, is relationship is undefined across processes that don't exchange messages. If two processes don't exchange any messages, no ordering. You can't say. Okay. Furthermore, even if they exchange messages, there are some events that will not get ordered. And we looked at that. After the send and before the receive, you can't order those events unless there are additional messages. Okay. So it's a partial ordering of events. This happened before relationship. Okay. So now we want a simple technique that will allow us to assign some timestamps to messages, not physical timestamps, there will be logical timestamp that allows us to actually implement this happened before relationship. Okay, this is just an abstract concept. Okay, how are we going to write some code to do this? Okay, so here is how we are going. So our goal is to define a timestamp for each event that respects those two properties. A happened before B, and the clock value that you assign to A, the timestamp you assign to A, has to be less than the timestamp of B. Okay, because A has happened before B, so the timestamp that we are going to assign to A by whatever technique has to be less than the timestamp of B. We want that property. And furthermore, if A and B are concurrent event, which means concurrent means there's no ordering, then we don't care about the time. So timestamp can be less than, equal to, or greater than. Okay, so the happened before relationship between two events, we want the timestamp to be essentially in that order. If A has happened before B, the timestamp of A should be less than. Okay, so we want to do this. How do we do it? Okay. So we are going to assign an integer value to each process that we'll call its clock. Our clock is an integer variable, not a real clock timestamp, it's just a variable. So we have an integer that we associate with each process in the system. Okay, that's our clock. Okay, so each processor, doesn't matter, maintains a logical clock. Okay, so the ith process has an integer LC of I. Okay, so how are we going to maintain this clock? Whenever there is a local event, you increment the clock. Okay, real clocks increment when a second or millisecond elapses. In our case, we only tick our clock when some event we care about has occurred. Okay, so you define what events you care about. Whenever that event occurs, new event occurs on that machine or that process, it's okay, another event occurs, so I'm going to increment the clock and then assign that clock value to that event. Okay, so it's an integer. So it's a, okay, I only, if you're just counting sending and receiving messages, those are the only event. Every time there's a send, I'll increment and timestamp. Every time there's a receive, I'll increment it. But you can use any events you care about that you want to track. Okay, so those are the events that will increment your local clock. Okay, now when process I sends a message to process J, you are going to piggyback your clock value with that message. Okay, the sender will always send their local clock value when you send a message. In addition to the message, the clock value will come with it. Okay, so when you receive the message, you have the receiver has their local clock, and there's a clock value that has come with the message. Okay, so you have your local clock value, but the message comes with some clock value. You are simply going to take the max of those two, add one, and then make the clock value as that value. So you take the max of your local clock, the clock on the message that came, so the max of the two plus one. Okay. So what that means is your local clock, when you receive a message, will always be greater than either the sender's clock or your local clock, because you're taking the max of the 2 plus 1. Okay, so essentially, When I sends to J, you piggyback, and then let's say if else, so this is just saying you take the max. So if you say your clock value is less than the sender's clock value, you take the clock value plus 1, else you do nothing, means you just increment your local clock, you don't do the math. Okay, and that's it. That's all you're going to do. And that's going to give you this happened before relationship. Before I show you an example, is it clear what we are doing? A very simple counting technique. Okay, so here are some examples. Okay, so 3 processes in this case, P1, P2, P3. Okay, so each of this time is going downwards. So those are the local clock values. Okay, it's not showing every single event that has occurred, showing some subset of event. Okay, so you will see that M1 went from P1 to P2, M2 went this way, and so on and so forth. Okay, so now when M1 is sent, M1 will take 6 with it because 6 was the clock value on P1. So 6 will come with M1. It comes to P2. Okay, P2's clock is already at 16. So it's going to take the max of 6 and 16, which is still 16. And then it will add 1 to it. Okay, so in this case, P2's clock actually doesn't change because of the send, because it's already added. Okay, now let's take M3. Okay, when M3 goes from P3 to P2, is going to take 60 with it because that's the clock one. Okay, so that is going to be received at P2. P2's clock is at 56. You're going to take the max of those two. Max of the two is 60. Okay, so this actually has to be set to 61. In this case, nothing has happened, but when you use the technique, this is what is going to happen. Okay, you will take the max of the two and you will increment that to 61. Okay, is that clear why it has to happen this way? Because the send has to have happened before the receive. So the receive cannot get a lower timestamp than the send. So the receive has to have the max of the 2 plus 1 as the timestamp. That's the only way you can guarantee that the timestamp of the receive has to be strictly greater than the send, because the send has happened before. Okay, and if you do this, you will see that every send has a lower timestamp. So M1 send has a timestamp of 6. Okay, receiver's timestamp is 60. Okay, so that respects are happened before relationship. The 6, that timestamp is lower than here. This one has 60, here is 61 for M3. That also respects are happened before relationship. Okay, so you will see now that local events, of course, you are incrementing the clock. So that's automatically respecting the happened before, but using Lamport's algorithm, okay, because we are now piggybacking the clock values of the sender and then doing the max of the sender and receiver's clock value at the recipient, you will always have a case where, or the situation where the receive timestamp is going to be greater than the send timestamp. Okay, yes.
We only care about the order, we don't care about the different value of each timestamp. Is it correct?
Yeah, the question is, we only care about the order, we don't care about the difference. Yes, so in this case, we don't actually care about the real time at which these events are occurring. We don't know the time at which M3 was sent, because we are not using physical timestamp. We only want to reason about events in a distributed system, in what order they occurred, not at what time they occurred. Okay? In many cases, that's good enough, and for that, this property is adequate. Is this clear? Okay, yes, question.
What if P3 makes another send like after M3, that like it just sends another makes a call to P2 and then on to P1.
Yeah.
So that would result in another increment in what P1 and P2. So
Yes, so you can send any number of messages. So the question is, what if P3 sends another message to P2 and then P2 sends another message to P1? That's fine. Okay, so you basically piggyback your clock value, it will do the max, and then you send that clock value to P1, it will do the max, and it will adjust the clock if needed. Okay, so that's fine. You don't only 3-4 messages are shown here, but there could be messages going back and forth. You use the same technique. Whenever you send your local clock. At the other end, you take the max of the message clock and your local clock plus 1. And that's all you need. Okay, yes.
So when a clock is being incremented, the next following ones are incremented accordingly. Right? So could we send like simultaneously more than one message?
Question is, could you send simultaneously more than one message from a process? That's your question, right? So in this case, if sending of a message is an event you care about, you are not sending anything simultaneously. Everything is in sequential order. It's only one core. Okay? It's not multi-core machine where there's actual parallelism. It's one core machine. So you are basically going to have to send a message one at a time. So simultaneous message sending from one process doesn't occur in this case because they have to be, one send has to happen before the other send because sequential execute. You could, in theory, send two messages from two different processes at the same physical time. But in this case, that doesn't matter from our perspective because our events on independent machine will cause some ordering, but that's okay. Okay. Is this clear what we are talking about? All right. So now you will see that whatever I was talking about, all the events before a send on one process will have lesser timestamp than all the events after a receive. Okay, so we have basically now started ordering events across machines. Yes, question.
An example A, machine 2, in between M2 and M3, are those events unordered? 32, 40, 48.
Okay, the question is on P2, you have events 32 to 48. Are they unordered with respect to what?
In general, just the machine's current state.
So all the events after the receive for M1, which is 16 onwards, everything, all they are ordered with respect to P1 send. So 0 through 6 on P1 have happened before 16 to 80 on P2. Okay, so I don't know if this works, but yeah, so this ordering does, so that ordering is respected because there is a send here. That's a send, that's a receive, that's a relationship. So everything before the send, which is here, and everything after the receive, which is there, is ordered. Okay. Now, all the events after 6, which is 12 onwards, they are not ordered with respect to these yet. Because there's nothing that has actually happened in addition to that one message. Okay. Question.
So there will be like some part of the timestamp in this case that don't make sense, but other parts they are older. So how do you tell which part of those timestamp make sense?
Okay, that's a good question. That was going to be my next question. So remember the property we are trying to achieve in this case is if A has happened before B. If I tell you that A has happened before B, then the clock value of A is less than clock value of B. Okay, we achieved that property. Okay, so if I show you a message, I say that message is actually being sent from P1 to P2. The clock values you assigned, all 0 to 6, those are less than 16 to 80. Okay, but the question that was asked is a good one. If I just gave you two random events, I say, okay, here take that event 30 on P1 and take this event 80 on P2. I just give you two values, say compare these timestamps. You can't say 30 is less than 80 and hence that event has occurred before the other event. Because there are unordered events that also have timestamps. So just comparing numerical value of timestamp does not allow you to reason about ordering of it. If I know the ordering of events, I can assign timestamps that respect that ordering. But if I give you two timestamps, I can't, looking at those timestamps, I can't figure out what we want. Okay. Ideally, you want the implication to go both ways. Okay. So if A happened before B, should imply that clock value of A should be less than B, but the reverse should also be true, which this technique does not allow us to do. Okay, logical clocks only give us implication in one direction. Okay, so we are going to generalize this. That's a good question because you can't just look at two timestamps and say, yes, the timestamp, I'm going to compare them. Right? So that doesn't work. But before we do that, I just want to say one couple of things, and then we'll look at a generalization that will allow us to do both. Okay, we can actually look at timestamp, and if there is a timestamp ordering that tells us what order the events occur. That's what we really want at the end of the day, to look at some timestamps and reason about ordering. But before we do that, here's a way by which we can take a partial order that we knew and then convert it into a random order. No, I shouldn't say random order. Convert it into a total order based on some random tie-breaking rule. Okay. So here is what we will do. So we will assign a process ID to each process, which is unique. Okay, so let's assume that we number all the processes in the system. Okay, processes are numbered 1 through n. Okay, within each process, we have a logical clock, which is an integer. Okay, that's the clock I just showed you here. So there are clocks on each machine. So there are 3 processes, there's a clock on each machine. So what we are going to do is we are essentially just going to attach the process ID to the process. Okay, so here to the logical clock. So the logical clock 1 value becomes 1.1, 2 becomes 2.1, because that's all on process 1. Okay, so here you have 1.2, 3.2, and things of that sort. Okay, so now this is just assigning some, because we don't actually know what has happened for unordered event, we'll just assign some rule saying we are going to order them from process ID and assume that's the total order, even though we don't actually know in many cases what the actual ordering. So this will just allow us to take a partial order and just assign a tie-breaking rule for the unordered event and let us get away with that and say that's our total order. Okay, yes, question. Okay. So we have logical clock values. To each logical clock value, we'll attach the process ID. Okay, process ID. So this process ID is 1. So logical clock values go from 1 to 4. We are going to attach the process, so it becomes 1.1. Okay, logical clock dot process ID. Okay, so 1.1, 2.1, and so on. So this one becomes 1.2. These clock values from 1 through 6 become 1.2 and 3.2, 4.2, and so on. And this becomes 1.3, 2.3, and so on. Okay, so we'll just do this, and then we will say our tie-breaking rule is you just take any 2 clock values, you just compare them, and basically if they're ordered, then this will still respect whatever was done because you're taking the max of the 2. Okay, but if they're not ordered, then this will just allow us to order them in some way. So if 2 processes both had logical clock value 1, okay, the one with the lower process ID has happened before the other one. So 1.1 is going to be less than 1.2 because they will either have 1 dot process ID and the other one will have 1 dot its process ID. So we just assigned a tie-breaking rule. Okay, this is not going to tell us actually what has happened, but it just allows us to say this is how we are going to order events for those that cannot be ordered.
So in this case, if you were to compare 6.2 and 3.3,
we'll say 6.2 is greater than 3.3, numerical comparison. Okay, even though that's not actually what may have happened.
but we can't say anything about like which event occurred first.
No, so first thing is this respects logical clock values. Okay, because that send will still always be less than this receive because you always took the max of the 2 clock values, right? So you took 4 and 6 and you took the max of the 2. So 4.1 will still be less than 6.1. Attaching process ID did not change any logical clock ordering. We just assigned a tie-breaking rule for values that did not have a way for direct comparison. Okay, so it's just a way to say for those that we don't know, we'll just add some value and then compare. You have a question? Someone there. All right. So this still doesn't tell us what we want. Okay, so we'll actually do a better version of this, but this is one way you can take Lamport's clock, which gave you a partial ordering. You assign a tie-breaking rule, which says that take any 2 IDs and 2 events. By attaching process IDs, we have a tie-breaking rule. So even if the logical clock values are identical on 2 processes, the process ID is used as a tiebreaker. Okay, so two events with value 3 on 2 processes will still have a tiebreaker because this is 3 point something and 3 point something else on some other process. Okay, that's basically the way you can take Lamport's clock and convert it into a total order. We will look at a technique that does better than this, but is one approach. Okay, all right. So this approach is actually used in database systems to actually get a total ordering of events. Okay, because you will think, if you think about it, you have ordering can occur. Ordering of events is a problem that occurs in many systems. Okay, you can think about your lab, for example, okay, that you just did. So let's say there are 2 clients in your lab 2 that send a buy request. Okay, when the buy request arrives at the front end, how do you decide which buy request came first and which one you should process it? Right now, you are essentially processing it based on order of arrival, right? Not order of send. So suppose that customer 1 actually sent the request first before customer 2, but just that customer 1 has a longer network latency. So by the time the request arrived, some other requests have arrived before it. Okay? But if you wanted to actually do ordering, you should then order the sends, not order the receipt. Okay? Because if somebody's pressed the button first, they should have gotten processed first, not order of receipt. But in your lab 2, you didn't worry about these things. You just looked at the receipt order at the server and said that's the order in which you process your request. That's fine, not a problem. But there are many other cases where you want to actually look at which one actually sent things. So that's this example here is showing that there are 2 clients, they're sending requests. So here is a case where you might actually have out of order problems because of this, because here we assume the database, there are 2 copies of the database, not 1. Okay. Here's customer 1, there's customer 2. Okay. So the customer 1 sends their order. Okay. Because this replica is close to this first customer, their order arrives first here. Okay. And customer 2 is far away, so their order arrives second. Okay. So the dotted one arrives second, the dark one arrives. Now on this other replica, the opposite happens. Okay. Because the customer 1's request is taking a long time to get there. Okay. So basically the customer 2's request arrives first and customer 1's request arrives second. Okay. So if each of these replicas simply ordered based on receipt time, you will have opposite effects because customer 1 gets processed 1 on replica 1 and second on replica 2. Okay. That doesn't always work because if you ran out of, let's say, a product, you are buying the last one, on one replica, you will assign it to first customer, another replica second, and you will have inconsistency. Okay. So in this case, you actually want to order them in the same way, regardless of how they are received. Okay. So you have to start reasoning about all these things. So you can solve this problem using Lamport's clocks and things like that. So we won't go into the details of how to do it, but you can assign each of these Lamport's clock values and then order them based on whatever we are talking about. Okay. So that's an example of why some of these things actually matter, why you want to also think about ordering sends, not just receives and things like that. Okay. But now let's look at, hold on, let me just go to this part, which is generalizing Lamport's clocks. Okay. So here, so we already looked at the problem of Lamport's clock. It gives us a partial ordering. And just looking at timestamp does not allow us to reason about the order in which we have. We had a hack which said assign process ID and we'll call that the tie breaking rule. But that's not really a good solution. But just a way to say that let's just try to get some ordering. And we said here is the tie breaking rule. Can we do better than that? Okay? And this is where we talk about how to do better. This part actually also talks about causality, which is the causal ordering of events. So essentially the problem with Lamport's clock was if A happened before B, we found a way to timestamp A and B such that the timestamp of A was less than timestamp of B. But the reverse was not true. Okay? If I gave you 2 events and their timestamp and say, look at these timestamps and tell me which event has occurred before which other event, we couldn't say. The Lamport's clock does not actually give you a total ordering that allows you to compare timestamps. So if C of A is less than C of B, we don't know what to say. Okay? But we would like to do that. Okay? We want the implications to go both ways. If A happened before B, the timestamps have to be respected. And if I gave you 2 integers and one is less than the other, you should be able to say, yes, this event actually occurred before this other event. Okay? If we did that, then we actually now can just simply start timestamping events with these notions of logical clocks. And I can just look at the timestamps and reason about events, which so far with Lamport's clock we can't do. Okay? So to do this, we will introduce this notion of causality. Okay? Causality simply says if A has happened before B, then A is causally related to B. Okay? It's nothing to do with causal inference if you heard of it, but the word causal is identical in both. Okay, so causal delivery here says that if the send of one message has happened before the send of another message, then you want the delivery to also respect that. So this is somehow ordering how messages are being sent and trying to respect order of sending and things of that sort. So in that banking example, if send of one message from one customer happened before the other, then the delivery will also happen in that order. Regardless how they are received, you will reorder them and deliver them in the same order. So if you have this property, you can do interesting things with it. Okay. So now all we need is a timestamping mechanism. So we know how to do Lamport stuff. We want a timestamping mechanism that gives us the second property as well. So if timestamp of A is less than timestamp of B, you should be able to say A has causally preceded B, which is like saying A happened before B. Okay. So how do we do that? Okay. So we saw generalization of Lamport's clock. Okay. And essentially we are going to use this notion called a vector clock. Okay. So our clock is now no longer an integer. It's an array of integers, which is a vector. Okay. So each clock essentially has n values. If there are n processes in the system, each machine or process maintains n integers, not one. Okay. Earlier our clock value is an integer. Now it's a clock. Each clock is an array, okay, of n. Okay. So I'm going to show a simple example. Okay. So let's say there are three processes, A, B, and C. Okay, so our clock values are essentially going to be integers. Okay, so three processes. So the clock essentially has three elements to it. Okay, so initially everything starts with 0, 0, 0. Okay, now we will have the same technique as before. All local events, okay, are ordered. Okay, nothing has changed from what we said before. So whenever there's a local event, each process is going to tick its local clock. So in this vector, okay, so we'll assume processes are ordered. In this vector, if your process I, the ith element is actually your clock. Okay, and the other elements are what you know about somebody else's clock. That's how you should think about it. So instead of one A, B, C, I'm just going to call this P1, P2, and P3. Okay, so there are local events here. You take your clock. Okay, so this is going to become 1, 0, 0. This is going to become 2, 0, 0, 3, 0, 0, and so on. Okay, in this case, you are going to basically become 0, 1, 0, 0, 2, 0, so on. Okay, and here you will basically go. So this is going to be 0, 0, 1. 0, 0, 2, and so on and so on. Okay, same as before, okay, except that in this case you're only incrementing one element of the vector, not all of them. Okay, when your local events. Okay, now suppose that there is a send, okay, from one machine to the other. So you send a message. Okay, again you're going to send your clock with the send. Okay, in this case you'll send a vector. Okay. Okay. So hold on. Just trying to go into handwriting recognition. Okay, so I think this is hold on. I'm just going to do a simple. Yeah, I think so. I used the. Okay. Oh, I need to bring the pen back. All right, sorry. Okay, so let's say here's a message that goes from P1 to P2. Okay, you have to send the vector with your clock. So let's say this was 0 to 0. Okay, so you're going to send 0 to 0 with the clock value. And let's say the one before this was it shouldn't be 0 to 0. It should. Should be 2, 0, 0. And let's say this was 030. Okay. So that's the local clock value here is 030, then the one that sent became 200. You are going to take the max of two vectors now, instead of max of two integers. Okay. Max of two vectors simply says you do element by element comparison and take the max of those two values. Okay. So that gives you the max of two vectors, and then you increment your local clock. Okay. So what's the max of 200 and 2030? It should be 230. Okay. So you take 230 and then you increment P2's clock. So it is going to make it 240. Okay. So this receive here is going to get a vector value of 240. Okay. And so on. So that's basically a technique. So whenever you have local events, you increment the ith value of your vector for process I. Okay. When you do a send, you send the entire vector with your message. At the receipt, you have the vector that came with the message. You have your local vector. You take the max of the two vectors, which means you look at each element and take the max of each element. And then you take the ith element of that vector and you increment that. Okay. So simple generalization of logical clocks. We did more or less the same thing, except that we are doing this to vector clocks as opposed to integer clocks. Yeah, yes. Question is, should this receipt be 340? Is that what you're asking? So you are going to take the max of the two. Okay, that's 200 and 3030. Okay, max of 2 and 0 is 2, max of 0 and 3 is 3, max of 0 and 0 is 3. So first you do the max, that gives you 230. This is process 2. So you increment the second element, not the first element. Okay. So you take that 3 and you make it 4.
Because in the previous case, if the clock only has 5 integer and your local clock is smaller than the process clock, you want to take the maximum and also plus 1.
Yes, so you're doing plus 1 to the ith element. Okay. So this clock value is actually less than the send. 240 is less than 200 as a vector. So you'll see that the property is still being respected. Okay, because now you got to compare vectors. You're not comparing individual integers. So I have not showed you how to compare vectors and say which vector is greater than which other vector. Okay, we'll talk about that. But first, let's understand what the technique does. Then I'm going to show. Okay, so let's go through the technique again. Here, update the vector clocks as well. Local events, you increment the ith element of vector I. Okay, process I is going to increment that. When you send a message, you piggyback the entire vector. When you receive a message, you essentially do the max of that, and then you do plus 1 to the jth vector. Okay. Now we want to say, let's compare two vectors, okay, and then see if the reverse is also true. Yes, your question.
So, given two vectors which basically correspond to time sum, so given any two vectors, if there is an increment at any element, say I index of both the vectors have a difference.
Yes.
So we can say that the event happened in the second vector, the event happened before the first vector. Is that what we're doing?
So I think basically now we want what we want is if timestamp of vector v1 is less than timestamp of vector v2, we want to essentially say that those two events occurred in that order.
So if we just take a look at if we didn't know that there was a message passing, we just know that 030 is a timestamp and 240 is a timestamp.
Right, so let's compare these two. I'll come to your example. Okay, 200, 240. These are two vectors. Which vector is greater? Second one. But you have to first ask what's the definition of greater for a vector. Okay. So that we have to first define for a vector what greater than means or less than means. Okay. So our relationship is very simple. We'll say that one vector is strictly less than another vector. Okay. If every element of the first vector is less than or equal to every element of the second vector, and that there is at least one element that's strictly less than. Okay. Is that clear what I said? So we'll say a less than relationship means every element has to be at least less than or equal to the second vector, and there's at least one element is strictly less than. Okay, so that's true here. Okay, so you have 2, 0, 0, 2, 4, 0. So these two are equal, those two are equal, but there's at least one element that's strictly less than 0, strictly less than 4. So we'll say that element is less than this element. Okay, so now if I just gave you these two vector values, you can confidently say that this event has actually occurred after that event. Right? I haven't shown you how, but you can actually say that. Okay? Now let's take the example that was asked before: 0, 3, 0 and 2, 4, 0. Okay? To compare this, you can ask which vector is greater. Okay? 2, 4, 0 has to be greater because every element of this is actually greater than every element of that, or greater than or equal to, but there are at least one element greater than. Okay, so again, you will see, you will say that that event that has timestamp 240 has occurred later, and you can see that that is true because in this case they're actually local events. Okay? In the previous case there was a send and a receive, but you could also order this. Okay, so we are beginning to get what we wanted, but you can say, what about unordered events? What happens to those vectors? Okay, so let's look at one. Okay, so let's take after the send, you have one that is going to be 300. Okay, so now I'll say, let's compare 300 and 240. Okay, so we have okay, so we are comparing 240 and 300. Which vector is greater? Okay. So remember, the less than relationship said every element of the lower vector has to be less than or equal to the other one. There's one, at least one that is strictly less than. Okay. So in this case, 3 is greater than 2. So the one element of the second vector is greater than the first one. And then 4 is greater than 0. So it's the opposite. Okay. So it's not the case that every element of this 240 is less than or equal to this. Neither is the opposite true. Okay. So these two vectors are not comparable. And that's exactly what we want, because those two events are not comparable. So because we cannot compare, as I said, after the send, you don't have an ordering between all the events after the send and here. That is why there is no way you can compare them. Okay. So whenever you have events that are not ordered in the system, they'll get vector timestamp that are not comparable. Okay. But when the vectors are actually comparable, it's guaranteed that those are actually ordered based on whatever the comparison tells you. Okay. So no more tie breaking needed. We are actually assigning timestamp that automatically tell you that these two events can't be compared. There shouldn't be any message going back and forth that allows us to order them. If they did, then they won't be compared. Okay. Yes. How, so questions, how do you choose how many elements in the vector? It's a good question. So we'll assume that the system is a distributed systems of n processes. Each process actually gets to have its own timestamp. So the vector will have n elements. Okay. So if there are 3 elements in the vector, that means this is a distributed system of 3 processes. If there are 10, that means a system of 10 processes, and so on. Okay. Now, there's one more subtle but interesting thing that I'll say, then we'll stop here, which is when I actually on process, any process J, if I look at the current vector, okay, so your local clock tells you how many events have occurred on your machine. Okay, that's how you're taking. So the jth element of process J tells you how many events have occurred on your machine. So you can ask, what do these other things mean? So this means that there are at least 4 events that have occurred on this machine, but what does this 2 mean for process 2? So any other element of that vector tells you the most recent event you heard from that other machine through some message passing. Okay. So in some sense, that's the frontier of messages that you have actually know about in the system. So when process 2 has a timestamp 240, you can be confident that process 2 has at least seen some message that has timestamp 2 on from process 1. That is why its clock value and there is 2. Yeah, exactly, because you're doing max for on a vector basis. Okay. you're automatically transmitting information about what is the most recent event from other process that you have seen. Okay, that's what your vector is actually telling you. Okay, and that is transitive. So you can now have P2 send a message to P3, and P3's clock will actually have, in this case, be 2, 4, something else. Okay, so that will mean that P3 now actually implicitly knows of a send with timestamp 2 on P1, because that's why its clock value is shown, and that is your transitive property. So you're propagating transitive properties through clock values as well. Okay, so whenever you get a vector, what that says is the jth element of that vector for process J says that's my clock, local clock. Okay, all other elements says what's the most recent send I have seen of a message from that other machine in the system, and that's what that clock value tells. Okay, that's a physical interpretation, but you don't need to worry about that. All you need to worry about is now clock values are comparable. If they are directly comparable, they actually imply an ordering. Okay. And if there is no ordering, automatically the vectors are not comparable, because you will have some elements greater, some elements less. So by definition, neither vector is greater than the other vector. Is that clear? Yes.
For the clarity, this vector is actually seen by the machine, and it's accessible by all the processes on memory, right?
So the question is, the vector is seen by the machine and accessible by all the processes on the one machine. So for this purposes of this class, the process and machine mean the same thing. We'll assume one process, one machine. There's no concept of two processes, one machine right now. Okay. But if you're asking if there are two processes running on one machine, each process actually has to have its own clock. So this clock is now maintained by a process, not a machine, because we are timestamping events in a process. So each process maintains a clock now, not that each machine maintains a clock.
So then how do we decide the size? Because you mentioned that the size of the vector needs to be the number of processes.
Okay. Question is, how do we decide the size? The size of the vectors, the size of the process. So first you have to decide what is your distributed system comprise. Okay. You don't want to take arbitrary processes on a machine and make it part of your system. Okay. This could be your client for lab 1, that could be your catalog service, this could be your ordering service. Just because you're running Chrome on your machine doesn't make it part of that system, because it's unrelated process. Okay. So you only take processes that are part of one distributed system or application. Those are the end processes. Other processes, there are lots of processes we won't get. Okay. Those don't need to be part of this system. Okay. Any other questions here? Okay. So there is a way you can formally prove now that what property we wanted, which is the vector of timestamp of event A is less than vector timestamp of event B, and A causally precedes B. I won't prove it. I showed you an example. Hopefully you are convinced that that is actually true now. Okay. Any questions on this before we move on? Okay, so we looked at two techniques. I'm just going to do a quick recap and then we'll move on. So we said no clock synchronization, no physical clocks. Yet we want to assign some timestamps to events and try to reason about events. Okay? So we use only two properties, okay? Local execution order on machines and sending messages from one machine to the other, or one process to the other. And we use that to derive an ordering. Okay, yes, question.
As a corollary, if you cannot determine the order of two vectors or two events via their timestamp, does that mean that you also know that they're unordered?
Yes. So the question is, as a corollary, if two vectors are not comparable, does that imply that they are unordered? That's also true. Yeah, I didn't say that here, but that is automatic based on what we did. Yeah. Okay. So again, just to recap, we said we are going to use two properties: local execution order on a process. Okay, sequential execution allows us to order events inside a process. Okay. And because you can never send a message before it is received, regardless of what timestamps you have and so on, we know the send is always going to happen before the receive. Okay. And we are just going to use transitive property to order the send and the receive. Everything before the send is now happened, everything after the receive. Okay. and we'll just use that to derive ordering. And we looked at two techniques to do this. One is Lamport's clock that just used integer clocks. Okay? It only allowed us to get one-way property where if you knew that two events were ordered, we automatically made sure that their timestamps were also assigned in that order. Okay? But in this case, the reverse was not true. You couldn't take two arbitrary timestamps and look at them and say, yes, this value is numerically less than that. So now I think this event has occurred before that. You could not say that in case of Lamport's clock. Okay? So to get that second property, we generalize Lamport's clock with a vector clock, where the clock is now an integer of a vector of n integers, not a single integer. Okay? And the ith element of that integer for process I is its local clock. That local clock works exactly the same as Lamport's clock. Okay? But you keep extra information to get that other property. So we did the same thing. Okay, we incremented the local clock when local events occurred. We piggyback the vector clock when you send a message. Okay. At the receipt, you now did vector max of two vectors plus incremented the ith element. Okay. And just by doing this, now we could also get the same property as Lamport's clock, but we also got the reverse implication where we could compare two vectors. And if they were comparable by the less than property, we were guaranteed that those two events have actually happened in that order. Okay. The reason this is true is any two events that are not ordered, you automatically get clock values, vector clock values that are not comparable. So you now essentially get the property you wanted. Okay, so that's our vector clock. Okay, neither of these two require clock synchronization. You can basically make integer clocks and essentially variables and processes that you are incrementing whenever you have an event you care about. Okay. All right. So that is vector clock. And this was an example which I am not going to go into. I drew lots of pictures, but it's essentially showing the same idea of doing max and whatnot. Okay, so let's just skip this in the interest of time. I'm going to talk about a different idea from clock synchronization, and this is called global state of a distributed system. Okay. So let me define what this is. And then I'm going to give you an example of why we care about it. Then we'll see one way by which we can capture globals. Okay. So what is a global state of a distributed system? A global state of a distributed system is the local state of each process in the system and all the messages in the system that are in transit, which means they have been sent and not received. Okay. So you take a system of n processes. Okay. So for a second, let's assume you pause the entire system. So time is standstill time. So nothing is executing. Okay? So you look at the memory state of each process. There's the state of that process. And then you look at all the messages that are in flight at that point. That's the state of that system. So if I were to snapshot that system in time, that's what I would get. That is what the system actually looks like at that point in time. Okay? That's the memory contents and all the messages in transit. Okay? Now we want techniques that allow us to save the global state of a system on disk. And you will say, why would you want to do such a thing? Where you might have all kinds of reasons where you want to recover that system. So say failure recovery. Okay? The one process in the system crashes. Okay? Now you have to restart your application. Okay? Will you basically throw out everything the application has done and restart it from beginning? You could do that, but then all the work that your application does is wasted. Right? So you want the ability to say, I'm going to checkpoint my state. Okay? So I have now saved a copy of that state on this. If any process crashes, I terminate all other processes. I then essentially restart the processes from the checkpointed state, and everything is consistent. I basically just start executing from that point on. Okay. So a good use case is essentially failure recovery. So think of another example. Let's say you are doing a long-running distributed simulation. Let's say you're doing machine learning training, okay, on a cluster. Okay. Many of you probably know how PyTorch and TensorFlow work. There are lots of processes. Okay, you're training a large data set. It's going to take you 2 days to do this. Okay, somewhere in the middle, one process crashes, okay, and you lose whatever it was doing. Now, what are you going to do? Okay. One option is I just terminate all of them, I restart from beginning, but all of the work you've done so far is wasted. All the compute cycles have been wasted. Okay. Instead, if this training system had periodically checkpointed every hour, it basically said, I'm going to write whatever I've done, my partial results so far, to disk. Okay. Then if some process crashes, okay, kill everything, okay, go back to the most recent checkpoint, which is like a backup, load all of that state and just execute from that point. And then basically everything you've done till that point is recovered, and then you only lost a little bit of work since the previous checkpoint, not everything you've done from the beginning. Okay. So essentially, this is one way you are going to take a snapshot of your entire distributed system. Okay. The question is, can we come up with a simple technique to make that snapshot? Okay. So how can we figure out the state of a distributed system? Again, okay, the problem is trivial if you had a perfect clock synchronization algorithm. Okay. Everything is perfectly synchronized. Let's say all clocks in the system are perfectly synchronized. Say, at the beginning of every hour, all processes should pause execution. So at noon, let's pause execution. Let all the processes write their memory contents to disk. Okay, let's write socket buffers to disk. Resume execution. Okay, problem is solved. And I now took a snapshot. Okay, but as you know, clocks are not perfectly synchronized. So if you say all processes should pause at noon, okay, that noon is going to be slightly different on different machines because their clocks are not perfectly synchronized. No clock synchronization algorithm is perfect. Okay. So now you have a case where one process, although its local clock says noon, maybe it's 1 past noon, and another machine is actually 1 minute behind noon. So you're actually taking snapshots at different points in time. So if you now take that snapshot and restart from that, that's not consistent because they're taken at slightly different times. Okay. You want to essentially take it at exactly the same time for consistency reasons. Is that clear? Why we care about this? So we'll assume that there is no clock synchronization. There's no global clock, yet you want to solve this problem, okay, in a way that is consistent. Okay. This will mean that you will take snapshots at slightly different times because there is no clock that's synchronized, yet you shouldn't do something that's inconsistent. Okay. So then you should say, what does it mean to be consistent or not consistent? Okay. For that, there is this notion of a consistent cut. Okay. And I'm going to explain that not with this picture first, but I'm going to use a simple example to explain it, and then we'll come back to this. Okay. So let's say, take a different example, not a distributed system. Let's say you want to take a picture of the sky with the camera. Okay. So we'll assume that the aperture of your camera is not large enough to take the picture of the entire sky at once. Okay. The sky is this too big, so you have to take a picture of the sky. Okay. Okay. But with a camera that cannot take the entire sky at one time. So what are you going to do? You are going to take a picture of one part of the sky, and take another part, and then you'll basically put them together and then say that's what the sky looked like. Okay. But now I want to say that you want to do this in a consistent way because you're not taking the pictures all at once. If you had N cameras, you put them together, took picture at the same time, you put it together, that's consistent view of the sky. But you said, I took a picture of this part, then I took a picture of another part, and I put the picture together. So then you say, what does consistency mean in this case? So let's say that there are some birds flying in the sky. Okay. So you're taking a picture where there are birds flying. This is like messages going back and forth and so on. Okay. So I take a picture here. I captured some birds. Okay. I take another picture there. I captured some other birds. So now I put all these pictures together and I say, what does consistency mean to you in this case? Okay. So first thing is you should have captured the view of the entire sky. Okay. All the birds that were flying should be at least in one picture. Okay. No bird should be in two pictures. You can't take a picture here. There was a bird. It was flying this way. When you took a picture here, it appeared here. So now you took the picture. The bird has appeared twice. Not consistent. Right? And neither do you want the opposite, where you took a picture here. There's a bird flying this way. And you took a picture of the sky here. The bird has moved out of sight. So it's in neither photographs. So you lost a bird. Not consistent either. Okay. So our consistency here means when you take a snapshot, this is actually a distributed snapshot, but you're taking real pictures, not snapshots on machine. So you want the consistency means that you have a picture of the sky where you captured the state of the sky. The state of the sky was essentially all the birds that are flying, such that all the birds are all captured in pictures. Every bird is in one snapshot. No bird that was flying is missing. Then we say it's consistent because you captured the state well. Okay. Same is going to be true here. Okay. We are going to essentially now take a snapshot of all of our processes. Okay. Memory state is not a problem. Memory state is like taking a picture of the sky without anything in it. You just capture that part of the sky. That's memory state. But it's the messages that are actually going to matter. Okay. So the first of all, if you had a perfectly synchronized clock, okay, these are three processes that are executing. You can tell all the processes at time t, everything should pause. That's at noon, they should all pause. So you essentially then have everyone checkpoint this state. That's fine. Yeah, that's like saying I took all the pictures. But that's not going to be the case anymore. So you have this dotted line here. And whenever the dotted line intersects a process, that means that process actually paused at that point. So this is noon on P3. That's noon on P2, that's noon on P1. There are slightly different times. Okay. Now, since there's checkpointing at slightly different times, what does it mean to be consistent? Okay. What consistency means are that all the messages in transit also have to be captured well. Okay. That means that every message that was in transit should be actually captured. You should not lose messages. So you should not have duplicate messages. Neither should you lose messages because you are going to replay them. Okay. So in this case, a cut is defined to be consistent if all the messages are either on the left of the cut completely or on the right of the cut, okay, which means all the send and the receive are all occurred on the left, which is before the dotted line, or on the other side. And if the message actually crosses the cut, which is M3 is actually crossing the cut, the send has to be on the left side and the receive has to be on the right side. Because the send has to have happened before the receive. We assume that everything before the dotted line is the word before your snapshot. Everything after the dotted line is something that has not happened. If you restore this process will start executing here, that process starts executing there, that other process starts executing there. That's what we mean by restoring. Right, so you want a case where messages in transit are actually captured by the cut and not lost. Okay. Now, on the other hand, if the receive, so here is an inconsistent cut. Okay, you will see that M2, okay, the send of the M2 is actually after the dotted line, and the receive is before the dotted line. Okay, the message is crossing the cut in the opposite way than this one. Okay, so you'll say, why is this inconsistent? What's the problem? Okay. So now assume that you essentially start this process P3 at where that dotted line crosses it, and then P2 starts here. Okay. So what is going to happen? P2 is going to start executing again. Okay. It will actually resend M2. Okay. P3 has already processed M2 here because you took its snapshot after it processed M2. So it's going to receive a duplicate copy of M2. This is like our bird that was actually captured twice. So it was sent and then it appeared somewhere else. You captured it again. We have duplicate messages. Okay. You don't want that. In this other case, if I didn't send M3, because it's a message in transit, it's been sent, you not yet received. If you then start executing P1, it's not going to send it again. It's already sent. It's going to start executing the point after the send. Okay. And P2 will start executing from this point on. It hasn't received M3. So if you don't replay M3, M3 will be lost. This is like our lost bird. You don't want that either. Okay, so you want to save M3 as a message in transit, which means you'll save the socket buffer. And you will essentially just start executing from that point on. So the message will get delivered. Okay. And in M2, you don't want to save M2. In fact, that's an inconsistent cut. You shouldn't even do that. Okay, because there M2 will get delivered twice, sent once, delivered twice, doesn't work. Okay. So you want to do all of these things in a way that allows us to capture a consistent cut. And this is consistent even though the clocks are not synchronized. You're saving the state at slightly different times. Yet everything should be just fine if you capture it in a consistent way. Somebody had a question.
Yeah, so I guess my question is, how do you, in the inconsistent cut, the message two is received by process three after, before the checkpoint, like the checkpoint is taken before it's sent on P2, so I'm confused on how that would
You're talking with a consistent cut, right?
be inconsistent.
Inconsistent. So what's your question? Can you repeat the question?
I guess how would P2 checkpoints before the send, but after the receive?
Right, so the point is, this is where the dotted line crosses the process, just means that that's the point at which you pause the process and saved it local state. That's all it means. Okay. So we are now taking an example where P3 checkpointed at this point where the dotted line crossed here, P2 checkpointed here, and P1 checkpointed there. And we are asking a simple question: if some process crashes and I just restart P3 here, P2 there and P1 over there, will that result in a consistent execution? And we are saying it will not result in a consistent execution because you are restarting P3 from a point where it's already processed M2. You are restarting P2 from a point where they are not yet sent M2. So if it starts executing from this point on, it will resend M2. And then as a result of that, P3 will get a second copy of M2 and process it again. This is like an order. We already processed an order, then the other process restarted from a point back in time and resend that order. So you've got two copies of your order. So you are essentially doing duplicate work, which is not going to result in a consistent. So what all this is saying is, if you checkpointed these processes this way, not going to result in a good execution. Okay, but if you did this, you will get a consistent execution, as if there's nothing had crashed and things of that sort. Okay. How to do this, we haven't looked at it. I'm just explaining concepts. All right. So we run out of time, so we'll stop here today. Continue this next time.